don't work yet.
It works. It's recording.
Okay. So, as I told you, today, again, the displacement method, but in a matrix form this time, because I told you even in the first course that the finite element method works if you have a code, a finite element program. You need also a computer, because without a computer we can solve very complex problems. Of course, for the course we will present some very simple problems which can be also solved by hand. But usually without a computer it is not possible to solve a real problem. And of course we need a user. You will be the future user or analyst which will solve some particular structural problem in this case, because as I told you, the finite element method is not a discipline, it is just a method, and it can be used also in thermal analysis, in fluid dynamics, in electromagnetics, and so on, in every discipline where we have some equation, we can use this method. So for today, let's say this is the course number 2, and I will use the book to present you the course, because I have not time to rewrite again for a better presentation. And first of all, we have some ideas here, some general idea, which I want to explain a little bit more exactly. So let's assume that we have a planar pin jointed frame, something like that. So some joints, and between joints we have some particular members or bars, if you want, and they are something like that, let's say connected. You can take something like that. Of course, if you will take some forces, let's put here a force here and another force, let's say here is to F, here is just F, we must have also some boundary. Let's consider a pin jointed here, and a simply support, let's say here. I will close my door, please. Okay, I'm home, as you, of course. And don't forget, we use a computer, we need a global system of coordinates in plane XY. And for this particular problem, we are interested in nodal displacement. That means how will looks the deflected shape, and also, let's say, in reaction forces, in internal forces in every member, and so on. And for that, we can imagine that initially we have some joints, as I used first. Between the joints, I have some members. Of course, it is possible to add more joints if you want. Let's say that here I will put on another one, which is not connected here. If you want, you can take here and another joint member, something like that. The loads may be due to forces, but the loads may be also due to the thermal load. And sometimes these kind of supports are not a rigid one. And instead of this kind of supports, I can have an elastic one, and I will consider a spring, but a little bit later. Let's consider first this one. And as I told you last week, for every node here, we can consider that we have some displacements which are denoted with ux, uy, dx, dy, or as in this book, the displacements will be denoted with capital Q. So here I will have capital Q and capital Q displacement along x and along y, and I will put an index here, x and y, and of course the displacement will be in every node. I will take more one here. This is qx and this is qy, and because we work on the computer, we must put an identification number for each node. So that means, let's say this is an arbitrary process. This is the node number 1, this is the node number 2, this is the node number 3, this is the node number 4, and so on, 5, 6, 7, 8, 9, and let's say 10. So we have 10 nodes. So this here will be qx for node 1, qy for node 1. This one here will be qx if we keep the same rule for node 8, q9 for node 9. And similarly, in every joint here, in every node, as you will see later, we can take some forces. And for the forces, let's use another color here. I will put, so it is possible to have a force here, will be the reaction at this point. And here the forces will be the external applied loads. As you can see here, we have not the load, but here we have one. And this one is negative because, as you can observe here, all the displacement and all the forces are positive if they coincide with the x and y axis. So here I can have generally a force Fx for node 1. Here I have a force Fy for node 1. Here I will have Fx for oh, so this is not 9, this is 8 here. 8. So Fx for node 8, and oh, sorry, the color is not good. Fx for node 8, Fy for node 8. So if you want, generally, we can build two vectors. Let's say a q vector. And let's put a bar here because this q vector is for all structure, or if you want, for all nodes. And that means I will have here qx, qy, and so on, qx and qy till the last qy. And this is what will be for first node, then for the second node, and last here will be for the last node. Let's consider the last node in this particular problem as 10, but instead I will put n. N means total number of nodes. And in this particular problem, this vector here will be 20 by 1, or generally, if you want, this one will be 2nn times 1 as the number of rows and just a column. Okay, if we take the forces, the external applied forces in all nodes, we can similarly define a new vector. Let's put capital F also with the bar because it is for the whole structure, and this one will be, let's say, the same. Please observe that we respect the rule. So this one will be Fx, Fy, Fx, Fy, and so on. The last will be Fy for first node, second node, and this one will be for the last nn node. So the main idea is to obtain something which will be useful for us. What? So let's imagine a very simple structure in which we have just a single degree of freedom. So in this case, every displacement means a degree of freedom. This is a simple spring, and if you have here a force and the displacement for this point will be x, so this is 1 degree of freedom system. You know that at equilibrium, this elastic force here is the stiffness of the spring times the displacement x. We want to obtain a similar relationship, but not for a single degree of freedom, for an arbitrary number of degrees of freedom. So in this case, instead of this relationship, I will try to obtain that the total external applied loads is equal with something times displacement. But we know displacement is this column vector, the force is this column vector, but we don't know this one. And this one, this capital K, is something similar with this one, but is in matrix form. According to matrix multiplication rule, because this one, let's say that in this case n is exactly to nn. So this one will be n times 1, this is n times 1, and to make the matrix multiplication, this one must be a square matrix, which is n times n. So the main subject for today is, okay, it is possible to write something like that. The answer, okay, it is possible, but how can we obtain this matrix? And then, for example, if you take a look, if we know all the applied loads, and if we know this matrix, capital K, with a bar, we can obtain the Q, which means the displacement. So how? We solve a linear system of equations. This is the idea. And now, let's go back at the structure, and let's imagine that this structure is built one by one element. That means if I will take a generic element here, so I told you that we can say that a particular element have or a typical element have an index E. So we can take this element E and we can say, okay, let's take this element, this typical element, and this typical element is an element which have an area. So the area of this element will be a, let's say, index E. The length of this element may be obtained is LE. The material for this element may be still, so we know the Young modulus for this element. Sometimes this index is here, E, you will see in upper part, but it's just a notation. Yeah? Don't imagine that this E is an upper number as 2.71 and so on. It's just a typical element. So the end nodes of these particular elements will be noted with I and J. So generally the end nodes will be I and J, but in theory, sometimes in the book, instead of I and J, I will not Professor Radesh used 1 and 2, but 1 and 2 are not these particular nodes. It's just instead of I, sometimes is 1, and here sometimes is 2. At the lab, you will see only capital I and capital J, the ends of the bar. So this bar is connected to another bar or connected to a joint. If we change an angle here, let's say theta for this particular member, we can obtain every element. So for example, this one corresponds to theta 0. This one corresponds to a theta which, as I told you last week, must be.
That is you want to lay that cover so thick it looks like 2 beads. This sectioning is awful.
Another course is here. I will yeah. So we have a student which can take 2 courses in the same time. So this theta, as I told you, is defined from the global system of coordinates, capital X and small x. Small x is from first node to the second node. So, for example, theta for this element here is this angle here, right? If this one is the I and this one is the J number. So, that's simple for you. Now, let's imagine that we put also at the ends here the displacement and forces for this particular element. So if we will do something like that, I will use this part here to make this picture as an introduction, because it's very important to understand these aspects here. So let's consider this generic element E. We can take here the nodal displacements, and also we can take here the nodal forces. So this one will be Qx for node I, Qy for node J. Sorry. This one is Qx for node J. This one is Qx for node J. And also the forces. This is the force Fx for the first node. This is the Fy for the first node. This is the Fx for the second node. This is f y for the second node. And the idea is, okay, if it is possible to write something like that, in this case we have only 4 degrees of freedom per element. And we can build a new vector, let's say Q for a particular element. And in this case, this one will be Qx, Qy, Qx, Qy for the first node, I and j, I and j. As you can see, it's easier to write Qx1, Qy1 instead of, so please keep in mind this rule here. Yeah. And also we can define a vector for forces for an element, which will be fx, fy, fx, fy for the first node and second node j. So if we define something like that, of course, again, it is possible to write in a matrix form a similar relationship. So you can write for an element, as you can see here, this is, Q is a stiffness matrix, you will see later, times Q for element. This time we have 4 degrees of freedom, so this one is 4 by 1, this one is 4 by 1. So if we put here, this matrix will be something 4 by 4, this is 4 by 1 again. And the idea is, okay, if I will be able to write something like that, and we can obtain this matrix capital KE. Capital letters are used for global system of coordinates. You will see later that the small notation, small letters, will be used for in local coordinates here. So another subject for today, okay, if we can write something like that, how can we obtain this matrix? And after that, because we have a number of elements from 1 to the total number of elements here, because let's say that this member here is member number 1, this is member number 2, for example. Again, not important. The last one here is the total number of elements, and it will be, let's say, how many elements? 1, 2, 3, 4, 4 again, 8, 9, 10, 11, 12, 13, and after that, again, 6. That means 20 elements in this case. That's correct or not? Yeah, maybe this case 20. If we keep the picture, but not very important. Yeah, and if we will be able to write this relationship, you will see later that we can use these 4 by 4 matrices to obtain this capital K with a bar matrix here, which is larger. So mainly this is the subject for today, and I will start to present you the course. So keep in mind this kind of notation, and after this one you will use also a new notation, because it's not simple to write here Qx, Qy, and so on. Sometimes you will have Q1, Q2, Q3, Q4 till the total number of nodes, but in the book a little bit later. So again, as I told you, the finite element method started with the displacement method. This is the main idea. But the displacement method can work if we use a computer, so we need the matrix form for all the equation. This is the idea. And as I told you, if we take a particular problem, something like that, yeah, we can imagine that the actual structure are connected to get into discrete joints. It's the same idea. So the relationship between the end forces, yeah, here, and displacement will define a so-called element stiffness matrix here. And this one, it's called global stiffness matrix, or sometimes the stiffness matrix of the structure, or in a new form, the unreduced global stiffness matrix. You will see a little bit later. Yeah, this is the structure stiffness matrix. This is K bar, this larger matrix. And of course, it is simpler to start with such a particular problem like a general problem of continuous material. This one will be discussed later. So this is the idea. And after that, the first subject is, okay, let's determine this one. How can we obtain this element stiffness matrix, which make a relationship between nodal forces and nodal displacement in matrix form? And for that, we must take a look at this picture. Of course, this member here make an angle, theta. But let's use another system of coordinates, a local one. So I will take x and y. And because we must keep a general rule, please observe that at these end nodes, we can have a force and then another force here. The new forces are denoted with small letters. And also we can have displacement along x-axis, which are denoted with small letters. And as I told you, instead of I and J, here you have 1 and 2. So this is, oh, sorry. Let's put the, and let's use the, okay. Let's use the red. Okay, so this I generally is, this one is I and this 2 is J. And please remember from mechanics of material, if you have a member here, and if you have traction, an axial force here, the elongation of this bar, let's put the length of the bar L, the elongation was N L divided by Young modulus and cross-section area. So you know this formula from mechanics of material. This formula will be used here. So, but as you can see, the F1 is minus N and the F2 is plus N. And this equivalence is here. And if we keep the notation in finite elements, the equilibrium for this bar means F1 plus F2 equal with 0. Please note that pin jointed bars can have only axial load, not shearing or bending. So if you will use this formula, you can also observe that this elongation is just Q2 minus Q1. And if you take Q1 0, this one will be Q2. If you will take this one 0, so that means you will fix in turn this point here or this point here. Yeah, you can rewrite this equation according to our notation as this form here, or as in this form here. And if we consider also this equation here, you can obtain these two equations, this one, yeah, here, which in matrix form, this is similar with this one if you want. In matrix form, we can write this one as this line here multiplied with this column give us F1. Yeah. And here we have another relationship between the end forces, which again here we can use a notation. For example, the displacement for this element in local system of coordinates means Q1 and Q2. The forces in local system of coordinates for this element is F1 and F2. Just a notation here. And yeah, we can rewrite, if you want, this equation something like that. So this is Q, this is Fe. So we can obtain this element stiffness matrix, but in local coordinates. This is the idea. So this is in element stiffness matrix in local coordinates. So we have something, but we need the capital K. This is the idea. And for that, the idea is, okay, we need to use the transformation from local to global coordinates. And for that, again, please put the typical bar in initial position and also in deformed configuration here. And if we identify the displacement in local system of coordinates, so this is Q1, this is Q2 here. This is Qx for node I or node 1, this is Qy. And from these triangles here, you can observe that from this triangle here, and also from this triangle here, yeah. And similarly here in this part here, you can observe that Q1 is this part plus this part here, that is Qx1 cosinus from theta, and this one here is Qy, this one sin from theta. So we have these relationships which are very simple, and after that you can rewrite these two equations again in matrix form, and we identify here a so-called transformation matrix. So as you can see, the transformation matrix, sometimes it is called the rotation matrix in mathematics, something similar with this one, sin cos minus sin cos again. Yeah, but this is the transformation matrix, which make a relationship between local displacement and global displacement. So in a condensed form, we can write this one in this equation here. So again, this is 2 by 1, this is 4 by 1, this is 2 by 4. Yeah. So for every element, we can know the theta and we can obtain the transformation matrix. If you know the nodal coordinates, this is not very difficult to be observed that if we know the coordinates for two nodes, 1 and 2, this is x and y. Yeah. You can obtain the length of the element as square root from the difference of nodal coordinates at power 2 square. Yeah. And after that, let's take a look at the forces. Again, the nodal forces for a pin-jointed bar element are along the bar axis. So F1 and F2 with small letters. If we take this angle here, and if we take the components of these forces along X and Y axis, we can rewrite again this very simple relationship. Fx1, for example, this one is F1 times, this is again theta, right? Times cosinus from theta and sinus from theta, and again in matrix form these four equations can be rewritten something like that. So again in matrix form we obtain a relationship something like that, in which this one is 4 by 1, this one is 2 times 1, and this matrix, this transformation matrix, is in transposed form. So in transposed form, this is 4 by 2. Yeah, is the previous one. The lines becomes columns. And after that, using matrix manipulation, I will omit to present that. You can take a look in the course, and if you will use the paper, you can demonstrate that it is possible to obtain this new matrix in which the global stiffness matrix is function of this transformation matrix. So the transformation matrix is something 2 times 4. In transform form here is 4 times 2. This is 2 by 2. So the element stiffness matrix will result 4 by 4. And if you will consider the expression for this one, please remember this one is EA divided by L for the Young modulus cross-section area and the length of a particular element times 1 minus 1 minus 1, 1. If you will do this matrix multiplication, you will obtain the element stiffness matrix in global coordinate. This is the main idea. So this is in global coordinate. And cos C and S means cosinus and sinus from theta. So we have this element stiffness matrix. So if I will go back in the first part here, yeah, as I told you, I was able to obtain this one. The question is, okay, can we use this element stiffness matrix to obtain the global stiffness matrix, and if possible, how? And there are a lot of possibilities to obtain the global stiffness matrix, yeah, using this general form here. So keep in mind that this is an important relationship, yeah, for us. And if you will rewrite again using the equation of equilibrium, you know, this is capital forces for element, yeah, these are nodal forces in global coordinates. So, and this matrix is symmetric, yeah, because cosinus square and sinus square are positive number. We can say, okay, along the main diagonal, all terms are positive or 0 if cosinus or sinus will be 0. And the matrix is symmetric, so we have some general properties for element stiffness matrix. And these properties are given here. So the element matrix is symmetric, the positive terms on main diagonal. The matrix will be singular, and its rank is only 1. So the order is 4, but the rank is 1. And if you add the line, the first line, this term cancel with this one, this term cancel with this one. So the sum of each row or column, if you want, because the matrix is symmetric, will be 0. So please keep in mind these general properties of the on element stiffness matrix. How can we demonstrate that? You can use the strength of materials, and if you define the flexibility matrix as the inverse of the stiffness matrix here, according to some theorems, you can demonstrate that the matrix may be symmetric. And another way is to use the mechanical work. So again, this is important. So let's remember just these equations here, which is useful for something else. But again, let's consider a single degree of freedom. Oh, sorry. So for 1 degree of freedom system, this is a linear spring, something like that. Force and the displacement x, the stiffness of the spring k. So as I told you, at equilibrium we have the elastic force is equal with stiffness times u. Please remember that the mechanical work for this one is in statics 1 divided by 2 times F times X. And the strain energy for this spring, which is denoted with capital U, is 1 divided by 2 kx squared. At equilibrium, the mechanical work is equal with internal energy. So if you take this term here and put in this relationship, you will obtain the equilibrium. So that is very simple to demonstrate. So why we need the mechanical work and the strain energy? Mechanical work and strain energy, this one and this one, are scalars. So a scalar can be added. And more than that, the mechanical work may be 0 when we have no force. And generally, the mechanical work is positive for a fixed structure. And the scalars can be added. This is the idea. In matrix form, it's a little bit difficult to define the sum of two different matrices, because please remember the global stiffness matrix. This one is n by n, and element stiffness matrix is only in this particular case is just 4 by 4. So this is the reason why we prefer to work with mechanical work and strain energy. And as you can see here, this is for 1 degree of freedom. For n degrees of freedom, this work is the displacement times the forces, or sometimes equivalent. You will see this one as 1 divided by 2, the force vector times the displacement vector. This is the same, but because this is 4 by 1, in transpose form will be 1 by 4. This is 4 by 1, and similarly here I must take the transpose of the forces. Here this is a scalar. And for strain energy, this relationship must be rewritten to be, let's say, 1 divided by 2 x times k times x. So it's the same. And the matrix multiplication here, as you can see, is this one. So this is more important for you. And please keep in mind that this is 1 by 4, this is 4 by 4, this is 4 by 1. So according to matrix multiplication rule, this is a scalar, the strain energy for an element. So using these ideas here, we can demonstrate that the element stiffness matrix may be symmetric. To demonstrate that the matrix is singular, we can use again the strain energy, and or you can use also the equilibrium, yeah, the equilibrium as in this picture here. So let's consider that in a particular case this is fixed, and this node here it is enforced to have only horizontal displacement. If we take this horizontal displacement as 1, so this is not a good idea to let's make a small picture here. So this imposed displacement is 1. Of course, if this imposed displacement is 1, I will have some reactions here. A reaction here, a reaction here. So this is, let's say, Fx, this is Fy in the second node, in node J. And the reaction here, to have an imposed displacement, I need a force here, which is Fx in first node. Again, instead of I and J, this is 1 and 2. And a new reaction force here, which is Fy for the first node. So this is the main idea. If we take this main idea and put in this equilibrium relationship, so only this term is non-zero. The remaining one will be 0. According to the matrix multiplication rule, instead of this number, here may be numbers which are non-zero, but they are multiplied with 0. This one is multiplied with 0. This one is multiplied with 0. So it's not important, the terms here. But Fx1 will be K11 times 1. So this is the reason why here K11 is this reaction force here. This is the idea. And if we will consider the equilibrium, this force here plus this force here must be 0. This force here plus this force here must be 0. So according to this one, the sum here must be the sum of this column must be 0. So another idea, because this is very interesting. So if we take in turn this 1 and the remaining 0, we can obtain the first column. If I will take the second term in this vector 1 and the remaining 1, 0, I can obtain the second column here. And using this very simple idea, you can fill all the matrix terms here, calculating only the reaction forces. The reaction forces here may be calculated using mechanics of materials. Yeah, you know, here the Moore-Maxwell method, for example. Yeah. This is the idea. Yeah. I will omit. And after that, we will take again, after the break, the previous particular problem which was discussed last week, and explain you how can we write the stiffness matrix for these three members, and after that, how can we obtain the global stiffness matrix. This is the subject for the next hour, but as a story, not using the particular notation and rewrite all the equation here. So in my opinion, it's a good practice for you to try to write yourself this kind of equation, because in my presentation I just point some very important aspects. We have not time because we have also the lab, and for the lab we must solve particular problems, and for you, it's very important to keep in mind just these ideas. So let's make a break for 10 minutes, and after that we will continue. Okay, may we continue? Are you there? I'm here.
Yes.
Yes, we are.
Okay. So let's discuss the same problem as was solved last week. So please remember, we have three members, 1, 2, 3, three nodes, 1, 2, 3. The external applied loads are, which are known, is this one and this one. The remaining one are reactions. Let's use a new notation here because it's easier. So as I told you, if you want, you can rewrite here the capital F for this particular problem means fx, fy, fx, fy, fx, fy for node 1, for node 2, for node 3, and instead of use this notation, it's easier to take f1, f2, f3, f4, f5, and f6. Okay, and similarly, if you want the displacements, maybe this capital Q bar is Qx, Qy, Qx, Qy, Qx, Qy for node 1, node 2, node 3, or you can use a new notation here as Q1, Q2, Q3, Q4, Q5, and Q6, as in mathematics if you want. Yeah, just a notation here, so a new notation. Yeah. Use that here. Again, please remember, all the Young modulus for all members was capital E here. The cross-section area for this one was A. The cross-section area for this one was square root from 2 times A. A is a parameter for area. And also here I have square root from 2, here is A. And the length, because this is given, and we know this angle here, and again this angle here is 45 degree, and this angle here is according to our notation. Don't forget this is capital X, this is Y. So if you want here, this is capital small x, this is capital X, so this angle here is 135. And we want to obtain the displacement along x for this node here because it is unknown. We know the displacement for this node along y, and of course we need the reactions. So this is F5, but F5 is known in our problem, okay? And this one is, no, this is F3, sorry. And this one is F6, right? We know this value as given. And again, this is according to our notation, yeah, the forces according to our notation. And if you want, generally, we can define a rule. If I will be 1, 2, 3, 4, and so on, you can obtain this general or notation here as, because sometimes in implementing something you need something like that. And after that, what we need to obtain? We need to obtain the element stiffness matrix K for a particular element, which according to our formula is Young modulus times A divided by length for each element multiplied with something 4 by 4, in which we have here cosinus squared, cosinus times sinus, cosinus times sinus, sinus squared, and this part here will be here with minus, also here with minus, and here with plus. So if you know this one, yeah, was written somewhere here. Let's take a look to see that. So this is our matrix. So again, we can use something like that, and this term is cosinus squared, cosinus times square, and this term here is for each member. So the idea is, okay, let's write these all element stiffness matrices, and for that we can build this table. And according to our particular problem, I will define again here. This is node number 1, node number 2, node number 3, and this is element number 1, element number 2, element number 3. So element number 1 or member 1 is between nodes 1 and 2. Element number 2 is between 1 and 3, and so on, right? The theta is 0 for the first one, 45 and 135. Cosinus from these angles are not a problem. Sinus again, cosinus squared, cosinus times sinus. The length of the members is L and square root from 2 divided by 2L for the element 2 and 3. The cross-section area times the Young modulus is here. So this term here is in front and was calculated. And here we have cosinus squared, sinus squared here. So we can write these particular matrices K1, K2, and K3. You can check that. And now, okay, the idea is, okay, this is for K1. It's a matrix which is 4 by 4. And also the second and third element stiffness matrix. But this one here is capital K, which is 6 by 6. And as you can observe here, this is very important for us. This is first, second, third and fourth degrees of freedom. So, or easier if you want, these two correspond to the node 1, these two correspond to the node 2. And also on vertical direction is the same. And also here, if you will consider, this is for node 1, this is for node 2, this is for node 3, this is for node 1, this 2 for node 2, this 2 for node 3. So here, where this was the nodes number. Okay, degrees of freedom will be 1, 2, 3, 4, 5, 6. Yeah, but keep in mind that the first two correspond to the node 1, the second two to the node 2, and so on. So the idea is, okay, if I will take a look, let's suppose that initially we have an empty K matrix, okay, and if I will take this one and I will consider in this large matrix the correspondence between the nodes here, or if you want the connectivity of this first element is in this position here. The points which are here are zeros. They are not written, but here we have 0, 0, 0, 0, 0, 0, 0, 0, and so on. All are zeros. The points are these particular values here. And also for the second element, so the second element is between 1 and 3. So again, if you want, this is for node 1, this is for node 3, this is for node 1, this is for node 3. That means, according to this rule here, this part here will be exactly here, and this second part here will be exactly here. And let's change this part here will be exactly here, and this part here is exactly here as position. So this one was observed first time. So, and the idea was, okay, this is a direct stiffness method because we can expand, if you want, this element stiffness matrix to a larger one, which is have some zeros here in this part. And similarly, you can observe for this one, okay, this is for node 1, node 2, node 3, node 1, node 2, node 3, these two parts, and this is 3, 4, 5, or if you want 2, 3, and again 2, 3. So this part here is exactly in this part here. And this idea was used to obtain the global stiffness matrix, if you want, just by simple add this expanded matrix one, yeah, to obtain the global stiffness matrix. So the idea is using this matrix of connectivities, if you want. It was observed that this matrix, capital K bar, is capital K for matrix 1, but plus capital K of matrix 2, plus capital K for matrix for element number 3. But this one, to be able to add that, because this one is 6 by 6, all of these must be 6 by 6. We cannot add a matrix, but we can obtain this one as some expanded matrices. And sometimes in this book, this expanded matrix, so which contain some zeros here and also here where you have some points, yeah. And we can obtain this one. Okay, after that, because this idea, according to the connectivity, yeah, this is a, if you want, a connectivity information, let's say, to n must be here, yeah. We can obtain this unreduced global stiffness matrix according to this idea, yeah. But later, yeah, you will see here all which I told you written. If you want to have a rigorously demonstrated form of this direct stiffness matrix, you must introduce a new matrix, which is this one, which is called connectivity localization matrix. So it is possible, it's very simple, to write that the displacement for one element here, which is this one is 4 by 1, can be written function of the global displacement, which is 1 by 4, which we take here a matrix which is 4 by 6 to keep the multiplication rule. And this matrix here, which is called the connectivity or localization or matrix, contain just 1 and 0. For example, for element number 1, which is between node 1 and 2, so this is for node 1, this is for node 2, this is for node 1, this is for node 2, this is for node 3. It's very easy to check that this line times this column is the same. Q1 is equal with Q1. So this connectivity matrix here contains just 1 and zeros. And for the first element here, this connectivity matrix corresponds to the element number 1. And we put a tilde to this one. This one corresponds to the second element, which also contains just 1 and zeros. And so on. This is for the third element. So we have a new matrix, which is the localization or connectivity matrix. So after that, using this is a second method for demonstration of the assembling process. What means the assembling process? The assembling process means that we can obtain the capital K with bar function of all element stiffness matrix. So according to direct stiffness method, we add this one, as I told you here. Or you can demonstrate that based on strain energy. So the strain energy is according to the definition, the capital Q bar times the here is first written in the local form, if you want. So the idea is that U for an element is 1 divided by 2. You can take the displacement for the elements in transpose 4 times this one times Q. Maybe this is in local system of coordinates. Maybe also 1 divided by 2 capital Q for the elements times capital Q times Q, and I need a transpose here. Or if you consider that the capital QE is the connectivity matrix times Q, and put this one here, you can observe that you can build a new matrix here in this product. So this Q here, in transpose form change. Please remember, if you have a product A times B transpose, you will obtain B transpose times A transpose. This is important to understand this relationship. Here, this one in transpose form, Q is in front. Here is Q bar. So you can consider this relation here, and this is the same. And in this form, you will define this expanded matrix here. So this expanded element stiffness matrix may be obtained according to the connectivity matrix and global stiffness matrix of each element. If you will do this kind of matrix multiplication as is done here, this is the, for example, this term here. Oh, I forgot. I can't. So this term here is K for matrix 1, right? This matrix here is the connectivity matrix for element number 1. And this is the transpose of this one, according to this relationship. And if you do the matrix multiplication, you will obtain the same. That means the non-zero terms for the first matrix will be here. For the second, let's close. For the second matrix multiplication, the non-zero terms will be exactly, where is here? This part here, this part here, this part here, and this part here. And for the last, this one, this one is exactly here. So the same result. So no something new. So in this case, the unreduced global stiffness matrix, according to these rules, using again this relationship here, but this time the strain energy is written using this global stiffness matrix. And if you put for Q bar and Q bar again the relationship which was written before, you can write this expression here, and we observe that the global stiffness matrix is the sum from E equal with 1 to the total number of elements of the element stiffness matrix. So to obtain the global stiffness matrix, write the element stiffness matrix, then we must do something to expand this matrix to have the same size. So this will be n by n, this is n by n. And add these expanded element stiffness matrices. So if you will add this one, you will obtain this one here, this matrix form. You can put this one on the computer if you want, and you can check that this global stiffness matrix is also symmetric. All the terms of the main diagonal are positive. The rank of this matrix, this is very important. The rank is n, in this case 6, minus r. R means rigid body motion or total rigid body motion. But plus mechanism motion. If you have, let's say, something like that, this is a mechanism. So to fix it, you need to add a more bar here. If not, you will have mechanism motion. So this is the idea, and this formula is general. In a plane or as rigid body motion are free. The mechanism motion depends on the problem. So, but in our particular problem, we have not mechanism motion. So we have only rigid body motion. But please keep in mind that this is important in practice. Another method to obtain this relationship is the joint force equilibrium. And what means that? Let's take a look again here. Let's expand all three elements here. And let's put the forces at the ends. According to our notation, this is Fx for element number 1, Fy for element number 1 for node 1 here, because this is node 1. And so on. Here, if we expand or if we split the elements, we can write the equilibrium for every node. So this length here is 0, but in expanded form, it's better to put a... And if you will write the equilibrium for node 1, then for node 2, and then for node 3, you will obtain these 6 relationships here. So, for example, F1 is equal with this force here plus this force here, because they are in opposite direction, as a force, applied force and reaction force, or they are internal loads. And as you know, internal loads are both pairs of loads, action reaction. So this one here, it's equal with this one here. This one here, it's equal with this one here. And we obtain this relationship. Again, if we take these all 6 equations, so we have 6 equations, and put them in matrix form, F1 is this line here times this column here. And here in this column, we have 3 vectors. This is F for element number 1. This is F for element number 2. This is F for element number 3. So, for example, F1, as you can see here, is Fx plus Fx, node 1, element 1, element 2. So, this 1 is multiplied with this one here. This one here is multiplied with this element here. Here we have 0. If we write this one, we observe that here is the first connectivity matrix in transpose form. Here is the second connectivity matrix in transform form. And here is the connectivity matrix for the third element. According to the matrix multiplication and partitions, we can say, okay, this matrix here multiplied with this vector here, plus this matrix here multiplied with this vector here, plus this matrix here multiplied with this vector here, give us the total force. So this is written again, this equation in matrix form, in compact form. Or again, we can rewrite here, because you know that the F1 is no, this is just a general form here, from E equal with 1 to 3 in this particular case. But generally, this 3 means total number of elements here. This is the idea. Then, if you take that this one is capital K times Q and put here, and then you take this to the connectivity matrix here and put here, you will obtain the same relationship for the force. So the same matrix here is sum of this expanded element stiffness matrix. So you can demonstrate, if you want, the assembling process. in using three methods. The first one was direct. The second one was the strain energy method. And the last one was the equilibrium or nodal equilibrium, let's write, because nodal. And we can write something like that. So if you write, for example, key A, for E equal with 1, 2 till the last element, assembling means that I will obtain this K bar as sum of K elements expanded. This is a general formula if you want, and it is valid for every element types, because you will see later that it is possible to use different members, not not pin jointed elements. So this is the assembling process, which may be demonstrated in this different method. And after that, we must take the boundary. We must reduce this global matrix, because don't forget, we have a relationship, something like that. But this one is singular. So we cannot obtain, for example, Q bar equal with the inverse of K bar times F bar. The inverse is denoted with -1. So this one is not possible to be obtained, because this is singular. We have not an inverse for that. This is the reason why we need here the boundary condition. What means that? According to this notation, the boundaries are in different form. The simplest one is that we know a displacement. So this boundary condition may include a so-called specified displacement of the supports. So generally, this specified means that we know a particular displacement, but usually this A small r0, that means in our case a point it's fixed here. So I have no displacement for this point here. Qi may be to 1 to the total number of supports here in this picture. Generally, there is possible to have a more complex relationship, something like that, but this one, for example, should be for, let's say, an inclined support, something like that, because the global system of coordinates is this one. Here between horizontal and vertical displacement, this is a relationship, a linear one, something like that. But usually in our problems, we have not something like that. But please keep in mind that such a relationship may be written in this form here. And the idea is, okay, if you will rewrite the equilibrium, you can take this boundary and you will obtain a new system, and this is some mathematics. If you want, I will neglect to present in detail. So the main idea is, okay, after imposing the boundary condition, you can obtain a new relationship in which here the element, the stiffness matrix is reduced, and that means this K without bar is polar. It is a reduced stiffness matrix. And this one is no more singular. This is the main idea. So this, if you will calculate the determinant, so this K minus 1 K can be obtained. So this K is non-singular. In which condition this K will be non-singular? Let's solve this particular problem. So in our particular problem, Q1, Q2, Q4, and Q5 are 0. Please observe that this is unknown, but here we know the applied force, and also here. So in one equation in which, so because we must take this one, multiply with this one, and we obtain, for one equation where we don't know the displacement, we know the applied forces. This is very important to keep in mind. And you can change the notation if you want. In practice, this is not done. Yeah. And you can put as the first unknowns in the first part. This is if you want as a permutation, if you want. You can observe that you can rewrite this one in this equivalent form, but all unknowns are first written. And here we know the displacement, and in this particular problem the displacement are 0. And if you will rewrite this equation in this form, you can observe that multiplying this matrix here with this term here give us these forces here, because this term here is multiplied with 0. Yeah. And you can rewrite this one in this form, and of course the determinant of this matrix here, so this is K for our matrix, will be not 0, because the determinant of K will be A divided by L, because this is a constant, times 2 times 2 minus 1 times 1. So this is 3, is no more 0. So we have an inverse for this matrix here, and we can solve the problem and we obtain the result. After that, if you take a look again at this matrix here, we can say, okay, this part here is denoted by KAA. This part here is denoted by KBB, for example, and this one will be KAB. And this part here is KAB in transpose form due to the symmetry of this matrix here. And if you will rewrite this equation in this form, you can observe that this line here times this line here is AF. We know these applied forces. From the second part here, if we know this term here, we can obtain the FB, the reactions. So generally in the theory, if you want, if we obtain the displacement, so we know this one because they are 0, and we can obtain later the reaction forces FB. So first, yeah, you can, so this relationship here means this line here times this column is FA. Then we put the unknowns Do you want to write this one? It's trivial if you want. Yeah, just you must write this line times this column give us F8. And you can obtain here the unknowns, which are the displacement based on this matrix here, which must be non-singular. In our problem, this vector here is 0. So in our problem, this is not present in our application. But generally, we can have non-zero displacement. Yeah, and in this case, this term is here. To obtain reactions, we must take, as I told you, the second equation, multiply this line with this column, give us the reaction forces FB. Yeah, again, and particularly for our problem, we can obtain here the reactions. After that, if we go back in the first part when we define it, please remember this equation. The elongation is this is the element Q1 and Q2 are displacements for this L, and of course the elongation is Q2 minus Q1 according to this is x, small x. And after that, if we take again the relation between local and global system of coordinates, you can take capital displacements, yeah, and theta here, and we can obtain the elongation, and using the elongation, then you can obtain the internal loads. And if you know the internal forces, you can obtain also the stresses. Yeah, please remember here that the stress in a member is T divided by A. And for a particular element, we must take the internal stress for this bar and the cross-section area for this bar. So it's just some matrix multiplication, or in this particular case, row vector times a column vector give us a scalar here, the reaction. Generally, in a more complex problem, you can also include the thermal loads. So please remember something as basic. Let's suppose that we have a bar which is free. Its length or initial length is L. Due to the thermal variation, or let's say in this, let's see a little bit later. No, it's L again. L for a particular element. Yeah. The thermal load, let's say delta T. Sometimes delta T is denoted just by T in this book, but please remember that usually you have a reference temperature and a new temperature, and the difference between new temperature and the reference temperature means this variation in temperature. And due to the thermal expansion effect, the length of the bar will be a little bit, I will have an increasing in the length here. And if you want this delta L due to the thermal effect is the thermal expansion coefficient times the length of the bar times delta T, or simple T. Yeah, is the same. If you will fix this bar, you will obtain an internal load in the bar, because the thermal load, yeah. So what means So this is the increasing of the length here. If you want to obtain the initial length, or generally if you want, let's take a bar which is fixed at both ends, and due to the thermal expansion I will have a longer bar, but if I will introduce here a force which give us or puts the bar in initial form, you can make this length, this elongation equal. So that means delta L from N must be equal with delta L from thermal load, and that means NL divided by AA. So this is N times L divided by EA. It's equal with this expression here, alpha L delta T, or simply T. L cancel, and you can observe that N divided by A is sigma. So you can say sigma, the internal stress, is EAT. This is a formula for this case here. And if you take, this is in local coordinates, if you take the element in a, and Ft here means N thermal loads here. This relationship in local coordinates, you can define this kind of loads, and you can rewrite, if you want, this formula in a simpler way. So this, the total stress, so this is the total strain, total stress in a bar will be due to external load and due to the temperature variation. This is the idea. Another idea, in just a few words, is okay, is the node numbering important? Generally, the answer is not. It's not important. The results will be the same. But in the last time, because the memory was a problem, this node numbering was considered in solving a problem. Why? Because sometimes if you use a proper numbering of the nodes, the global stiffness matrix, so capital K with bar, may be in a particular form. So very large number of member in this matrix will be 0. And in this case we say, okay, it is possible to form a band matrix, and this is the called the half bandwidth of the matrix B. And this one is 0. Of course, this is symmetric, and in the memory it's possible to keep just this kind of information here. This was demonstrated, and for example, as a practical rule is, okay, if I will use this kind of numbering of nodes, this one is better than this one in which I will use, for example, this numbering. I will show you how looks this one when we will start to solve a problem. And you can read. Another idea is to use so-called skyline method, or skyline storage of the stiffness matrix. And the skyline is due to the reason, as you can see, Sometimes you can have non-zero terms on this line here. So this is as a skyline. This is the idea. This one is 0, 0, 0, 0, according to different numbering. So again, just a few words, and after that we stop. In matrix method, we have the geometry of the model. We know the material property, cross-section area. We know also the connectivity and boundary condition. This is the input data for a particular problem. Then we can write the element stiffness matrix in local system of coordinates, and in local system of coordinates, this was notated with small k. Then we transform this one in global system of coordinates using the transformation matrix, which is this one. Then we are assembling the global stiffness matrix unreduced as the sum of Ka, which was these times expanded. We have also a formula for expanded matrix, which is similar with this one, but with tilde. Yeah. After that, we consider the boundary condition. So usually that means some Qi will be 0 for particular degrees of freedom. Then we obtain this kind of new system of equation, which K is no more singular. So we have this one. This is important to know. And first we obtain the displacement. So from this equation I will have Q, the inverse of this matrix, times the external loads, which are, this is known. Yeah, and these are nodal displacements. And after that, we can obtain the reactions. So the reactions are obtained after we obtain the displacement. This is the main idea of a direct stiffness method in matrix form. Yeah, it's after the break, we will discuss some problems. You can solve as a particular problem even this one, which was presented, but I will take a new one because as you know, at the labs you must solve some particular problems, and for today we will use a finite element truss code. It is loaded in the Moodle platform, so please download this code here, and you will obtain please use Shift Control plus to rotate if you want the problem. So this is the problem for the student number 1, problem for the student number 3, 2, and so on. You will be able to solve this one, but because I need to give you a lot of explanation, this is the first problem, I suppose that you will not be able to finish in 1 hour. So my question is, when you will be able to upload the results for this particular problem? Today till, let's say, 2 p.m. or in maximum 1 week. It's your choice today. But starting with next week, when you will be able to solve the problems directly without my intervention, just for some simple question. Yeah? I will consider that better is to solve the problem and load after the lab. So not 12, but let's say 1 p.m. or 2 p.m. maximum. Because if you will omit to solve and present the problem, you will lose the points for the lab. And that's not good. I told you that for the first two labs, I checked only 7 labs. So if you will omit to give me the labs, you will obtain 0. 0 point from 10 is for each lab. So for the first two was 1 point. So don't neglect this aspect. It's very important. If you will have, for example, 5 from the lab, you will pass. Just you must be present. This is the idea. Again, if you will solve the homework, if you will have the presence also at the course, and you participate at the exam, and again you will solve and you will answer at the theory, you can improve the final mark to 10. But the lab is very important. If you want to pass, you need minimum 2.5 from the labs, so half from the labs. Of course, in the last 4 weeks, you can improve the number of points for the lab, but as I told you, the last 4 labs will be more difficult because the same problem must be solved in this MATLAB or Octave codes and also in ANSYS. So this is optional if you want. So if you lose now, you can, let's say, in the last 4 weeks to improve the labs, but try to finish in time. So think about that, and after the break, we will discuss also this subject because it's important. I suppose that I can even load the subject in Moodle platform right now, or even here it's possible, to download from, if I will take here the subject for today because it's easier. Let's put here. Don't work. It works. Please download, take a look, keep the same number. If we have new students, I will give you supplementary number after 23. I don't know if in the future 24 till now, but we have 28 problem there. So let's make a break for 10 minutes, and after that we will discuss. And think about this lab. If you have the solution right now, I will accept today, because let's say that it's the first lab or first 2 labs, and we take them later. But generally, if, for example, for the homework, if you will be late, you will lose some points. So from the maximum, you will obtain just a part. So please solve in time. This is a good idea. Break 10 minutes. Are you ready for the lab?
Yes.
Okay. So first of all, everybody have a number? Please,
Wish we have.
please consider. If not, let's check on the Moodle platform, because it's important. So our course is where is my? So dynamics of machinery will be discussed with Professor Angel, but I see that it is in my. So in the first we have the group, which was still that. Then a new student have 24. He's here right now.
Yes, I am here.
So, okay, please keep it. Another students have problems with the number. We have new students. So I will check later, because I saw that there are more two students. I don't know why in the platform. So let's take a look at the problems. Our proposed problems are this one. As you can see, they are not very complex. For this one, for example, you can take the first. If you have time, you can also solve for the big case. It's the same, just these diagonals are changed to be a little bit different. This is the idea. As you can see here, the node numbering is also done. The element numbers must be introduced by you. And as you can observe here, for example, this problem here, you have two elastic supports. So that means here is a spring. Then for other problems, as this one here, you have a spring, and you have also an imposed non-zero displacement here, which is 1 millimeter in this case. For problems as this one, for example, some members, some elements are thermal loaded. So for example here, the element which corresponds to the nodes 9 and 2, where is 9? 9 and 2, these elements have a thermal load of 50 degrees Celsius, right? Also the element 7,6, which is 7,6 is this one, yeah. If you have not as given temperature, that means there is not a thermal load, as here, for example, just two springs, or here, or even here, you have a lot of elastic supports for this problem. For example, here you must be very careful when you will obtain the nodal coordinates, because this is a equilateral, or is not an equilateral triangle, but this is 45 degree LL, so this is a circle if you want, and they are equally spaced along a circle. To obtain nodal coordinates for a circle, please put the origin, the system of coordinate just here, and of course L times cosinus from 45, yeah, and sinus times cosinus from 45. It's not a problem for you. And also for this one, as you can see, the nodes are along a circle, and put the origin here. It's a good choice. Here you have also two cases. You can take just one, the first one, or if you have time, both. Just you must change some diagonals here, as you can see. And I will take a problem which is a complex one, because as you can see, we can have thermal loads, we can have also elastic supports, and I will mix a problem which will have all these kind of loads. Yeah. Thermal imposed non-zero displacement, zero displacement, or pin jointed or simply supported. So please note that this kind of picture permits horizontal displacement, and here is a imposed, so this support here is enforced to have a vertical displacement d1, and this enforced displacement is negative if you will take x and y, and also this one is also negative on this direction here. Here also we have an imposed non-zero displacement in this problem, and when you have temperature, you can also have the thermal expansion coefficient. This is for steel. The Young modulus is also for steel. The spring constant is given in Newton per meter. The units is your business. You can take Newton and millimeters for all, but you must transform kilonewtons to newtons. You can take Newton and meter, yeah, if you want, but all units must be the same. Here is a mix in the units, so don't put the numbers something like that, because you will obtain mistake. So the program which may be used for today is this finite element truss. Truss is the name of the element type, which is pin jointed element in 2D in this case. As you can see, in every directory will be a main program. The main program may be main truss, as in this case, or maybe just the name of the directory. For example, okay, I suppose that you will be able to run the Octave. You can change the directory, copy and change directory, or just if you will double click on file here, all these files are M file. So all are M file. Their extension is M. Let's open, for example, this and double click on it. We'll change the current directory exactly to this directory. Is no more necessary. So, and this is the, don't change the programs, because if you will make some modification, you will obtain mistakes. This program is an old one, as you can see, was written by Professor Radesh till 2006, right? Of course, here we have a lot of files which are used for this main code, or main file if you want, and we have a lot of files which start with X from example. So this is an example file, another example file. This is the example for the problem which was solved at the course. And I will take, this is X-link as name, and more one X-link 1, I don't know why. And minimum 1 hour. I will explain you in detail how we can use this code, and similarly for the next week when we will change the code. Please observe that in the platform okay, no, here. Already you have this one. For next week you will use this one. Then 2 weeks I will keep the same code. So here pull frame will be again used. Then we will discuss grid, and after that I will consider again after verification, because in this new Octave version it is possible to be some difference, and I will check first the code and after that I will load here. So you can download and you can also try to check. So let's start. First, it's a good idea to run the code. So from the command line window here, yeah, you must type the name of the program, and this is mine trust. Yeah, we have it somewhere here, mine trust. Enter, and oh, sorry, mine trust, enter, and the program asks for an input data. I will take xlink without m. And the program reads this file and give us total number of nodes, total number of elements, degrees of freedom per node. That means this displacement along x and y. So we have 2 degrees of freedom per node. Then total number of nodes per element. So each element have 2 nodes, I and j. And then total number of different materials in the model. In this case, we have a single material. For this material, number 1, we have Young modulus. Young modulus is just 1 here. This is not correct, because Young modulus for steel, for example, is 2 times 10 to the power 5 megapascal. The thermal expansion coefficient alpha is 0. Why? Because in this problem we have not thermal load. You can keep 0 or you can keep a non-zero value, will be not important for the final results. Then you must use enter, as you know, and you can see that you have some new information. Restraints and nodal coordinates. Nodal coordinates means coordinate x and y for each node. What means bx and by? I will explain later. The idea is bx means blocked degree of freedom, and we have 0 or 1. 0 means degree of freedom is blocked. 0 means degree of freedom is free. It's non-zero and it is not known. This is the idea. You will see in the picture. And nodal coordinates here, we have just the number and the numbers, neglect the units for this simple problem. Enter again. You will see some information about element data. So we have 3 elements. The end nodes are capital I and J. And for example, element 1 is between node 1 and 2. Element 2, node 1 and 3 is the same as in the course. Element number 3 is between 2 and 3. The cross-section area, the parameter A was 1. So the first is 1. This is square root from 2 times 1, and it have a new cross-section area. All the members are from the same material, and we have not thermal loads in these elements. So the thermal load or increasing in temperature, yeah, plus T means increasing, minus value means decreasing of the temperature. This is the idea. Enter again, and we obtain first the picture of the problem. And as you can see, this point here is fixed along X and Y. We have, this is our problem. This is simply supported only along Y. Here we have a force, this is 6F, and this is 9F. You can observe here that in node 2 I have 6, F is also 1. So in this first problem, the length, the area, the Young modulus, and the parameter F all was considered as 1. Yeah, it's just for the first run of the problem. Yeah. So here you have the number. Here you just see that here is a force on vertical direction. This is fixed along X direction. So if you will see here, the node number 1, which is this one here, it's fixed along X and it is fixed along Y. So it is blocked along X and it is blocked along Y. This node 2, it's free along X and it is blocked along Y. This node 3, it's fixed along X, 1, and free along Y. Yeah. The element number 1 is between 1 and 2. Here is the number, but this color is a green one, I can see very well. So this is 1, 2, 3. Cross-section area is here. Now this is the force, no prescribed displacement. That means not non-zero imposed displacement. This is the idea. Enter again, but we must put here mouse. So, and after that we obtain the solution. So nodal displacement and nodal reaction or nodal forces are given here. So node 1, it's fixed, the displacements are 0, but for node 2 along Y direction I have, here I have a displacement 1 and here I have a displacement 4. If you go back at the course and you will check after the solving the problem here, oh no, here, this is 1 times this FLEA was 1. So this is 1, this is 4 times 1. So also we obtain here 4 and 1, the displacement. And here we have the reactions. The reaction in node 1 is minus in opposite direction of the x-axis. Minus 5, minus 4, 6. 6 is given load. 9 is also the given load. And here we have minus 5 and minus 1. If you will go back in the course, you have the course. You can check that the reactions here are minus 5, minus 4, minus 5, minus 1. Yeah. Minus 1, minus 5 here. So the results are the same. After that, you will obtain a new picture in which you will have the deflected shape. So with dotted line, you have the initial configuration, and with the continuous line, you have the deflected shape. You observe that this node 3 have a vertical displacement, a plus 4 in our case. This one have a horizontal displacement, which is 1. And after that, you have the internal loads. The internal loads means the forces, the forces in each member. So they were also obtained here. So the tension or the force in element number 1 was F, that means 1. This one was 4 times square root from 2. And this one was 5 times square root from 2. But the cross-section area for the element number 2 was square root from 2 times A. So the internal stress will be 4. And you can check that the reactions are according to this solution here. As I told you, this was 4. It is 4 also here. And more, one enter, you have a general information. The maximum or largest stress is 5 here from this vector, and it is in element number 3. So you will obtain all the information, but the input data file must be correct. If not, you will have wrong result. Also, here, after solving a problem, you can close the picture. Okay, it is possible to enlarge it. You can also move sometimes. You can zoom out or zoom in, yeah. And sometimes you will see that the bars are no more plotted. This is due to Octave. I checked last week and I found not a mistake in the code. The code is good. The problem is due to the Octave. Sometimes the bar are missing here. Try to check the zoom in, zoom out if you have not the bars. With red here, you can observe that this is more stressed element, element number 3 in a picture. This was the last picture, last file. So when we use it, this warning is due to the MATLAB. I don't know why. So let's take a particular problem and let's solve it, and after that you will be able to solve yourself. Okay, I told you that this is the second lab may be finished in maximum 1 week. If you want to finish today, is better. If not, let's say that 1 week is good. But starting with the next week, you must finish in the same day. So let's say, because we have you have not another activity till 12, I will consider, let's say, 1 or 2 p.m. the deadline for the lab. If not, we will discuss a little bit later if you consider that this is not a good idea. So for all codes, you will have some general input form of the truss, and you can observe here that the input format is given. This is one idea to take a look at this file here. Or if you will open, let's say we run the X-link. If I will open it, you can see that the inputs was given using a lot of vector and matrices. For example, general data. General data, or in Romanian, date generale, date gen, yeah, means total number of nodes, total number of elements, degree of freedom per node, number of nodes per element, and how many different materials. So if I have one material, I will have just one line here for material number 1, Young modulus and thermal expansion coefficient. So better is to take a look here, because here you have also an example here for this input data file. So total number of nodes, total number of elements, degree of freedom per node, number of nodes per element, total number of different material. for each material. Young modulus here is steel. Thermal coefficient, which is also for steel, this one. But here in this, the units means Newton and millimeters. Then for each node, we can observe that you have data nodes. Here is data mat. You have node number, blocked code along X, blocked code along Y, which means 0 or unknown displacement, and coordinate X and Y for node 1. Here is 0 and 0. Then data LM for each element, you have two nodes, I and J, cross-section area, material number, and thermal load. In this case, you have, for example, 50 degrees. Then we have something new, data arc. This is for spring data. So arc means spring. For each node, you can see that we have a stiffness along X and the stiffness along Y. The units must be consistent. So if you use here Newton and millimeter, this stiffness will be Newton divided by millimeter. You can transform. Also, the stiffness may be along Y direction. If you have not springs, you just will put an empty matrix. This one, and remove this one. As is here, for example. Data arc is an empty matrix or empty vector. After that, you have data force, or that means applied external. And for each node where you have a force, you must put force along X and force along Y. Here the force along X is 0, we have only force along Y axis. Minus means it is in opposite direction to Y axis. If you have not external applied forces, you must take an empty matrix. And after that, you have so-called non-zero imposed displacement. Here, data D plus. Data D plus means non-zero imposed displacement. And where we have a non-zero imposed displacement, you can take node number. And for example, here, only vertical displacement is -3. -3 means -3 millimeters, for example. And this one is 0. If this one is 0, that means it is not imposed a vertical and horizontal displacement, because 0 was already specified here using blocked degrees of freedom. Okay? If you have not imposed non-zero displacement, you must take 0. And that's all here. The program here may be used for check how was implemented. If you have time, yeah, you must read it. Let's take a new example. For example, what we have here, X arc X P. Let's take a look to see a file which is larger in size. Almost all are smaller. XP6, XP6, yeah, will be. As you can observe, but if you will double click on another file, you will open again Octave. So I will close this one. Let's run this one, XSP6 as a new application. It is here. So in command line, again, main truss, you can use, arrow, and let's put the XP XSP6 as the name. Of course, this is a large problem. Yeah, gain all the information. Now the young modulus is the real one, and as you can observe here, the units are meter and Newton, because here young modulus is at power 11. These x and y coordinates are in meter, small numbers here. The cross-section area is in meter square. No temperature load, also for this problem. And this is a similar one which I drew at the beginning of the course. So this point here is simply supported. And here is a this is a point which is fixed along both directions. It's a fixed articulation. This is a simply supported just along x, you can see. And here we have a force in this node for this particular problem. Of course, center, you have the displacements in meter, again in meter. And after that, the deflected shape, it's normal because the force is downward, the displacement is something like that. The reaction forces, the stresses, more 1 enter, and the largest stresses in pascals. And it is in element number 20. If you will take a look at the picture here, this element was plotted with red. So the most stressed element is this one, 20 in this example. And now I suppose that you will be able to solve a problem, but I will take a problem which is not very complex, but also not very simple. I will use also this file. Let's add a new empty page. Where is it? Class here. Oh, what's that? Huh. It's the first. Let's go at the last one here. And let's discuss the lab. Number 3. So I will start with a particular application. Let's suppose that we have a structure with no very many elements because we have not time.
Could you do something with spring?
Sorry? Please.
Something with
is not clear. Oh, how can I write this one? I have a tablet. This was the question. So I use a tablet for that. So let's suppose that this point here is completely fixed.
She asked you if you could do a problem with a spring.
Sorry?
It's from home.
Do you want to take a problem from this one?
Right.
She said with a spring.
I will put springs here. Just a moment. I will take here a vertical spring. I will take a complex problem. Also here an horizontal one. No, I will take a problem which have all types of loads. Here I will put a simply supported point. I will consider, for example, in this point here, displacement, a non-zero displacement here for this point, let's say, let's put the node number 1 here, node 2, node 3, node 4, node 5, node 6, node 7, and node 8. So I have total number of nodes 8. And here I will take V8 equal with, let's say, 0.5 millimeters. So this point is enforced to have a vertical displacement which is not 0. Okay? And this point is enforced in this direction, in opposite direction of y-axis. Of course, we need a global system of coordinates. I prefer to put the origin here in this node 1. The origin is not important, it's your business. After that, let's consider again that some elements, let's say these two elements here, have a temperature variation which is the same. This is, let's say, temperature variation 2, 4. It's equal with temperature variation of 4, 6, and it is again 50 degrees. Okay, so we have blocked degrees of freedom, we have springs, we have imposed non-zero displacement, we have thermal loads. So all kinds of loads was introduced until now. Let's denote this. Sorry, let's change the color. So let's put for this one ky because it is along the y direction, and this is kx. Okay, and again, let's suppose that all the elements have the same cross-section area, and I will take 100 millimeter square. Let's suppose that all the elements have the same Young modulus, and this is, let's say, steel. This one is 2 times 10 at power 5 megapascal, because here is gigapascals. Okay, and how many elements? We must put a number for every element. Let's use this color, and this is an arbitrary process, as also the node numbering if you want. So let's say this is element number 1. You can put it in a this is element number 2, this is element number 3. Then let's put here element number 4, this is element number 5, this is element number 6, this is element number 7, this is 8, this is 9, this is 10, this is 11. Don't miss one element because this is 12 and this is 13. So this is the last one. The total number of elements will be, according to our 13, and this is 8. Okay, all the members have the same cross-section area. Here, this is the Young modulus. Then the thermal expansion coefficient is the same for all members, and it is 12 times 10 at power minus 6, 1 divided by Celsius degree. And again, we need the geometry. Let's suppose that this is a small a, and all these coordinates are according to this picture, I will take a small a. So let's say that small a is 0.5 meter. That means 500 millimeters. And this imposed displacement is given 0.5. Let's suppose that kx is equal with ky, and it is equal with k, and this is, let's say, 2 times 10 to the power 6 Newton per meter, yeah, because maybe even larger, but let's keep something like that, because here is a meter. Here I have to transform. I have 1000 millimeters, so this is Newton per millimeter. So from the start, I decided to use as units for this problem Newton for forces and millimeter for dimension. If you change, you must put all the inputs in the same units. The students mix the units and make mistake. This is not good. So please be carefully for in the future. So we need more inputs. I think that is no more necessary to have another input, so we can build the input data file. So let's try to make this one smaller. I need a picture somewhere here for the problem. I will keep like that, and here let's keep the input data file. It's a little bit this one may be closer. Oh, why? Due to the code. And this is possible to be larger. No, this is the page layer. I can increase the size, I suppose. I don't know very well this program, but it works. So to develop this particular problem, we need a new file here. My opinion, a good idea is to, after keeping in mind this one, you can take an existing one, or you can start from zero. I prefer to take, for example, this one. And this one is will be saved as a new name. Let's say demo. Just a moment, I need to change my glasses because I saw that I can't see very well. So now it's a little bit better. So demo from lab. Yeah. Save in the same directory, and let's make the modification. X, instead of X link, I can put X. Not important the name here, because as you can see here, this is the comment. So data gen, first number is total number of nodes. We have 8. Then total number of elements. We have 13. then 2 degrees of freedom per node, 2 nodes per element, a single material also in our case. Material number 1, first is Young modulus. Young modulus is 2e5. Thermal expansion coefficient is 12e minus 6. After that, node number 1 is this one. It is blocked along x, it is blocked along y. So we can also make a, oh, sorry. Why don't work here? I need to, let's see. So for something like that, that means bx is equal with by, and it is 1. It's blocked. So please keep in mind this. A free node means bx is equal with by, and it is 0. A simply supported something like that means bx 0 and by is 1. It's blocked along y direction. And if you have, for example, something like that, that means bx is 1 and by is 0. I suppose that till now it's clear. It's just a code. So go back here. So node 1 is fixed and fixed. It corresponds here, and 0 is x and y coordinates. It's okay, it's the same. Node number 2. Node number 2 is this one. Is fixed along x. So I need here 1 and 0 along y. The x coordinate for this node 2 is 0 along x and plus a, but a is 500, so I need here 500. I will try to increase the size. Let's see here, debug run preference. No, what's that? It's run. I will try to increase the, not works. Can you see the
we can see
editor?
the code. We can see the code.
Yeah, it's clear. I can't see very well. Font size. But this is for command. I need for editor. Where is number of size? The editor. Yeah, this one. Let's put larger. I hope. Okay. No, don't work. I don't know. I will try later. Okay. Node number 3. Node number 3 is this one. So this one is a free node. So we need to put 0 and 0. The coordinates along x, it is 500, and 0 along y. After that, it's a good idea to copy the node. So Control C, Control V. We have 8 nodes. So this is 4, this is 5. I need more. This is 6, this is 7, and I need more 1. Control V. I will remove this one. Delete. Work. Okay. And also you can put here the last brackets for this one. So this is node number 8. So node number 4 is free, 0, 0. And the coordinates is 500 on x, 500 on y. Node 5 it's free, and the x coordinate is 2a, that means 1000 and 0. Node 6 is also free, and x coordinate is 1000 and y 500, that's okay. Node number 7 it's free, yeah, you can have motion there, and the x coordinate is 1500 and 0 here. Sorry, this 1000. No, 7 is 150 and 0. This one is also 0, and I will check a little bit later. So let's check. 5 is 0, 0, 6, 0, 0, 7, 8. All degrees of freedom may be non-zero, and even here I have an imposed non-zero displacement. Here I must take 0. Date LM. Date LM, we have element number 1 between 1 and 3. So element number 1 between 1 and 3. Material is 1. Yeah, let's take a little bit here. So for each element, date LM. So the end nodes, cross-section area and material. Cross-section area is the same for all, and it is in this case 100 millimeter square. And material is material 1, and the element number 1 have not thermal load. Only in these two elements I have thermal load. So I will keep 0. I will remove this one because I have all the elements here with the same cross-section area. Yeah, copy again. It's a little bit, you are younger and you will work quicker. So element number 1, let's put here element number 2, element number 3, element number 4, element number 5, element number 6, element number 7, element number 8, element number 9, element number 10, 11, 12, 13, and that's what I have, 13 elements. And let's modify the nodes. Element number 2 is 3, 5. The question is maybe 5, 3. Okay, it's the same. You can change if you want. Yeah, it's the same, not important. Element number 3 is 5, 7. Element number 4 is this one, 2, 4. Five is 4, 6. Is 6, 8. 7 is this one, is 1, 2. Is 3, 4. Usually we take as first node the smaller one, but it's not a rule. 9 is 5, 6, or 6, 5 is the same. But and 10 is 7, 8. Is the first diagonal is 1, 4. 12 is 3, 6. and 13 is 5, 8. Okay. And the same cross-section area, yes, as you can see, the same material number 1. I have also thermal variation in element number 4 and 5. So in element 4, I must take 50 and 50 element 5. Only here I have thermal loads. Then I will remove here. In this matrix here, I have connectivity matrix. I have cross-section area for all members. I have material number 1, and I have also the load for element data. Let's put the springs according to input data file format. For each node where we have a spring, we must put the stiffness along X and Y. Here I have only one spring in this model, but in my case I have spring in node number 7, and I have spring along X and spring along Y. Please note that all times this spring constant or stiffness of the springs must be positive number. So in our case, for this one along X and Y, I have the same value to E5 and to E3. External load applied forces. So we have no applied forces here, but I will take 1 or 2. Oh. Why? I don't know why. The program give me, and here I have no more. The page we must take, but let's go back and let's put also some external load because it's important to have also. Let's suppose that here I have only a force in node number 5. And for this force, I will give a value. Force is 5 kilonewtons. That means 5,000 of newtons. That's correct. So, in which node? In node 5. Let's put here in node number 5. Of course, along X it's 0, but along Y here it's minus 5,000 or 5E3, it's the same. No more forces we have. Only one here. It's enough. If you have more, you add more lines. So I will remove this line here. And date de plus. That means non-zero imposed displacement. I have one. Where? Here. In which node? In node number 8. So in node number 8. And according to this format here, you can see the X and the Y, the displacement. So let's complete here. I have not imposed a displacement along X, so I will take 0, and this V it's in opposite direction of this Y, so I will take minus 0.5 millimeter. And that's all. You must save the file, go in command window, and let's type truss again using, oh no, it's main truss. The name of our file here was demo lab. Please note that MATLAB is case sensitive. Please respect. Let's check number of nodes, 8, 13, it's okay. Degree of freedom is the same for all. One material it's good here. Enter. Blocked. Node 1 is fixed, that's okay. Node 2 it's only on X, that's correct. The remaining one are 0. Nodal coordinates, I will see why it's here in my, yeah, I will check that in the drawings, in the picture. Element data 1, 3 and so on, the same area, it's okay. Material, only 2 elements here, yeah, it's okay. So I will check the connectivity here. So as you can see, the picture is okay. This node is fixed, this is simply supported. Here with Chan we have thermal load, it's okay. Here we have the springs, that's okay. Here I have an imposed displacement, it's okay. And here I have a force. But the force is red and you cannot see very well here. We can see something, but not very well. Let's try to change the where is now it's better, I suppose, right? So force, the non-zero displacement, thermal load, springs. You can use also zoom in, zoom out if necessary. Yeah, you can also obtain a larger picture. As you can see, here is a mistake. This is due to the octave. Yeah, if you will try to or move something like that, it is possible to have mistaken plots. You can keep the, yeah, okay, as you can see, some warning is due to the octave. And after that, I will obtain the displacement. And after that, here, the force is in all nodes. So I have the solution. Enter again. You can see the deformed configuration, something like that, due to thermal loads, the force here, the imposed displacement here. You can check, for example, that the displacement for node number 8 along y direction is minus 0.5. It's okay. But this one is not 0. It is 0.3 millimeter. Reaction. We have only one imposed load, this one 5000, and non-zero forces here are reactions. You can take them from the results. If we examine the element results, for each member I have internal forces, T, in the course, and here the stresses. Okay, usually we need the stresses. The largest one is here, but the program tells us. So the maximum is in element number 13 and the value is 62 megapascal. So again, 1 hour for this problem, but with a lot of explanation. This file I will upload in the Moodle platform or even here in this one to have access on it. So let's see, where is my last file? This one. I will put exactly here to download if necessary. It is. You can run yourself. Now let's take a look at your particular problems, and if you have some questions for me, you can ask. So for this one, just a spring, no imposed nodal displacement, just one force here, the input data, yeah, and the molar force here. So, in my opinion, you can use the paper, and it is better. After solving the problem, you must answer to these two questions. Where is the maximum nodal displacement? And you must take a look at the deformed shape, for example, in our problem. If we take a look here, you can see that maximum is somewhere here or here. Here it's 0. Yeah. And if you take a look here in the nodal displacement, which one is largest? So this is minus 0.5, but this is 6.7. This one is 4, so the maximum is here in this one, node 5. This is smaller, this is smaller. Yeah. So maximum in absolute value. Neglect the minus. For example, in our problem, if you want, the answer is okay for this one. So maximum displacement is in node number 6, no, this one, and the value is ux or dx for node 6 and uy for node 6. So the value was minus, what is here, minus 6.79, then minus 1, minus 11. And this is minus point, not 11, let's check again. Yeah, that's correct. If you want, you can keep more than 2 digits for this is 7, 9, for example. But this is the largest one. And the maximum stress or maximum axial stress is in element number. Let's check again in the program here. 62 in element 30. This is the answer for this particular problem. So you will try to solve on a paper. After that you can make a copy, and please send me PDF file, because this is better. I can open, for example, a PDF file and make the correction directly on the PDF file. If you want to send me Word or another files, there is not a problem. So this is an imposed displacement, this is an imposed non-zero displacement, springs, and here you have coordinates in meters, don't make mistakes. Yeah, and here is not a problem. For example, you can use square root from 2 also in the code if you want. It is possible to put here in code instead of f. Yeah, square root is, you know, in MATLAB it is possible sqrt from 2, for example, or equivalent, you can take 2 at power 0.5. Yeah, it's the same. You can put without calculation. Also, it is possible to work with some parameters here. If you want, you can take capital A here, for example, yeah, equal with 100, and instead of 100, you just put capital A. Yeah, it works. I'm not sure if you have a different. Let's check another example. This is my example, old one. No, just number, not very important, but you must keep in mind that sometimes it is possible to have some parameters. No. So, a lot of time for the first time. Next week, we will have something similar. Instead of pin jointed bar, we will have beams, so rigid connected bars, and just a few modification in the input data will be presented. So you must work home this time because we have just 20, let's say maximum 20 minutes. In 20 minutes you cannot finish the problem as the first one. Of course, the problem may be also solved in a finite element code as ANSYS, but I will omit for today. I will show you next. If you are interested in this kind of problem, you can use the documentation which I suppose that I loaded in the platform. Let's check here. You have something about ANSYS here. Not? There is something which is interested in ANSYS. It's better for you, but let's show you.
Sorry, I have a question about 17, the problem.
So please share the screen.
Okay.
And I don't know why I can't hear well. There is some interruptions in.
Is about this problem 17.
So please enlarge it, make it larger because I can't see. Not there. You hold the window.
Don't know how.
Okay, yeah, okay, that may be okay. I will try to understand.
I have a question about T63.
Yeah.
It's the same temperature for 6.5 and 5.3.
6.3. I can see 6.3. Maybe
It's
a
here.
mistake. So you have 2.4. 2.4 is this one, right? 4.6 is this one, yeah? And it's 6.8 here.
It's 8.
It's 8.
Okay.
It's a mistake. We have not 6.3 is this one. We have not.
All right. Thank you.
Just here. No, it's a mistake from the subjects. Yeah, they was written by Professor Radesh. They are older, but the students are also in each year are different students, so not a problem.
Okay.
When we I'm not sure, but if we will work at the school, I will print the subject, I will cut them, and you will take one. Now, because we work online, you must have a number, and the number is given.
Okay.
So another questions.
That were my question. Thank you.
Please transform all the units. Use
Yeah.
a coherent or consistent system of units. You can take Newton and meter or Newton and millimeters. Yeah. Strength of materials, I suppose that you use a Newton and millimeters. This is the reason why I keep these units. New questions, please. So, and now let's discuss the first lab. I'm not sure if you check it here. You check it this one. I put here also the marks.
We cannot see your screen.
Oh, sorry. Yeah, that's correct. Sorry. So on the platform, yeah, you have the 6 labs were loaded here, and the student sent it me by mail. And one student sent it by mail, and also he loaded here. And I saw the labs, and if you want, let's check here.
But I think we can't see them because it is restricted.
Is not possible. So I have all the subjects here. We can open, and the mark is here for. So let's take a look. For example, Andrei Alexandru, just half. He have some mistakes. Andrei George, just 0.9, almost 1 from 10. Gabriel Dascaliuc, only mistakes, 0.1. Juana Claudia Martin, it's perfect. This is 0.3. This is perfect. Anca Bianca and Andrei Gabriel Stanescu, it's perfect. So, which one want to see? Let's say Andrei Alexandru, because he obtained only half. Andrei Alexandru. So in the future, please note that here is a bad mistake. Here is good, but this one is positive for every cross section. So that means here is a mistake. I don't know where, but if I see here minus, that's not good. This is good. Yeah, this is good, but this one is not. This one is not. It's a very important aspect. This one and this one is positive, and this one plus this one give us Ix plus Iy, if you know from strength of material. Let's open Stanescu, for example. He had 2, which was this one was the last. So it's 5. This is the correct value from my results. It's closer to this one, it's closer to this one, and finally 75, it's almost the same. As you can, only this point here is not, this digit is not perfect. This angle is minus 80, and no, it's minus let's see the problem. It's 0, 90 and 0. But here I can't. I cannot see what it's with this one.
But why have
Okay.
you give me just 0.5 when I mistake just two variables?
Because it's very important. An engine,
Okay.
yeah, don't take, as you can see here, yeah, across in this one, it's something positive. Only the cross product may be negative. Yeah, this is the reason. We will be engineers, and we must.
Can you please show me what mistakes I had?
Right,
Ciobotaro?
right. Let's open. Oh, I have here the results. I can show you, for example, very quickly. Now this is for full, for quarter, and I have here the same results as for you, all of them. Yeah, and let's close this one, and let's go to the. Oh, not here. Ciobotaro, where is Ciobotaro?
The second one.
Okay. Oh, this is the wrong geometry.
Why?
I don't know. Let's check. Here, the coordinates for node 4 and 3, it's wrong.
Why?
It's simple. So this is the correct result here, as you can see. It was plotted to have a... And as you can see, the results are not very different.
The angle is a lot different, but all my angles were almost the same.
Yeah, the results are closer to this one, but your results are larger because the y coordinates is no more L. Please excuse me, I must take this for just a moment. I will close the. Oh, where is the plot for? Vă rog să mă scuzați, dar era un telefon pe care chiar trebuia să-l iau, că acum fiind cu perioada
Nu nicio problemă.
de
Domn profesor, eu am verificat datele problemei și coordonatele și sunt corect.
s-ar putea să fie greșeala la mine. Dar hai să deschidem problema și să vezi că greșeala e la dumneavoastră, da? Deci
Sigur.
mergem aici pe back. Săptămâna 1 și care era problema, era asta, da? Și tu aveai hexagon.
Numărul 10.
Da?
Da.
Ia uite-te aici. Ai pus originea în centru, da?
Da.
Da. Hai să vorbim în română. E mai simplu. Deci, coordonata punctului de aici e 30. Ai luat-o bine, de acord?
Da.
Coordonata lui ăsta pe orizontală este jumătate din 30. Ai luat-o 15, ok? E,
Da.
coordonata asta pe verticală nu este jumătate din 60, adică nu-i 30. Da? Trebuie să faci sinusul unghiului și să vezi cât îți dă, că ăsta e un hexagon regulat. Așa cum vezi. Ai luat
Da.
jumătate din... Da? Deci eu mi-am dat seama că n-ai vrut să o faci, da? Dar nu puteam să-ți dau maxim pentru că rezultatul nu e la bun.
Da, nu înțelegeam cum n-am luat-o bine. Da, în capul meu erau egale, da.
Păi nu. Asta e. Vezi că din fiecare greșeală trebuie să mai înveți ceva. Deci nu e nicio...
Da. Mulțumesc.
Altcineva care vrea să mai vadă. De regulă vor să vadă cei care au greșit. Da? Oana, mi se pare că, nu știu, ea a făcut parcă bine. Da. Are febră, n-am ce să-i comentez. Uite, rezultatul care e corect, rezultatul ei, da? Sunt, dar ultimul e bun. Da? Aici sunt erorile de discretizare. Eu am numai rezultatul bun, că nu le-am făcut încă o dată, da? Și eu. Și cine mai avea? Stănescu era bine, Dascaliuc a văzut. Nu, Dascaliuc, uite ce, nu știu ce a făcut el aici, a făcut altă problemă.
Altă problemă?
Asta era aiurea. Deci tu n-aveai asta cu gaură, da? Care e numărul tău?
13.
Da? 13, unde e 13? Da? Deci nu le schimbați, că dacă le schimbați faceți altceva și dacă e altceva, ia uite, 13 e asta. De unde ți-a apărut ție problema aia? Da? Nu e aia bună.
Nu trebuia să luăm doar un sfert de cerc, practic, din toată...
Nu, puteai să iei din motive de simetrie, puteai să iei jumătate.
Jumătate, ok.
Dar tu ai făcut numai bucățica asta.
Da.
Da? Și ai pierdut zona asta. Deci ai schimbat problema cum ar veni. Da? Atenție pe viitor. Da? Aici se poate lua un sfert, uite să și marchează aici. Aici nu era marcat, dar și la asta la fel. Jumate se poate lua dacă nu vrei. Aici tot un sfert, unde e marcat. Da? Dar nu renunți. Da? Așa, ai făcut altceva. Ai făcut ceva care... Da? Deci, pentru astăzi, că teoretic s-a terminat acum lecția, e cineva care nu înțelege română, să vorbim în engleză? So, for this lab, try to finish it. How is better, to send it by mail or to load it in Moodle Plus?
On Moodle, I think.
Okay.
But can't we choose
I will put the deadline for this second, let's say second lab, next week. Let's say next week, Wednesday at 8 p.m. when we start the course. So no after the course.
Okay.
Okay, but please keep in mind that you must understand, try to work, because the next program you will have access to it. Now the next is pull frame. Yeah, you can open a run main pull frame. Try from time to just main pull frame or type here data taken input here. Let's say XB1 for example. And you will see something similar. I must to increase here. And again, pictures. Yeah, simply supported beam, not simply supported, elastic supported beams. Yeah. And another idea which must be kept in mind for you, because some problems may not work if you have time. Let's close this one. Oh, okay, no problem. Why? It's working, not possible. I must finish. Format, structure, and again, you will see no axial diagram, but you will see shearing diagram force here, bending diagram here, yeah, and so on, reactions. And for some particular problems today, for example, this is okay, this is okay, this is okay, this is okay, can work, also this one. But for the problem, this is okay, this is okay, okay again, this is okay. 17, there is the student for this problem. He is absent. For this one, you have rigid body motion. So one point along X must be fixed because, as you can see, yeah, this stiffness is working only on vertical direction, and on horizontal direction we have not supports. So this is have a rigid body motion. So you must fix an arbitrary point along X.
So doesn't matter where?
Yeah, for example, okay. Better, let's say 0.5. 0.5 okay. It's fixed along X. And you must check after that the reaction force here is 0. Because if you fix a point, you will have a reaction. If you will fix just to remove rigid body motion, the reaction must be 0 or very, very small. This is the idea. The remaining program will work without problem. 24 is the same. As you can see here, the equilibrium, it's okay, but you have a rigid body motion along X. So the node 1 must be fixed, but only along X axis. Yeah. This is okay. Okay, this is okay. So this is a trick which I will explain later, but you must correct this problem. So better is to load the I will create, but after probably today, but later on Moodle on a new assignment for lab number 3. Okay. So more question if you have. If not, I will take again the presence for the lab. And more question. If not, see you next week, starting at 8 o'clock for the course. And as you can see, is not very simple. The theory is complex. If you want to understand, you must take a paper and write everything and try to understand. Unfortunately, if you want, the problems are simpler, but not the codes. The code is already written, but you may use it. I told you that it's a good idea to read something about ANSYS. I have here an ANSYS for students, and if you have time, take a look at this file. Is the last one, which was you have not access on the ANSYS I will put it here, and also the course I will save and I will load. What I suppose that, okay, I must activate this one. Try to read this one. Because this one, you will see a lot of important information about ANSYS. Yeah, this is the ANSYS. You know it. Some explanation, command line. I have no time. It's not in your curricula to learn ANSYS, but you have no more finite elements. So for the diploma project, it's a good idea to try to understand something right now, and after that you will be able to use. I will also load the course, right, because after that I must go. So this is our course here. I will save because it's also the lab. It is in, okay, here. Oh, it was the PDF file save. I will check that. So this was the course presented with a lot of annotation here. If you want, you can read the book. I can also give you the initial form if you want, without modification, and the lab is here. Yeah, this particular problem, the input file you have. So let's put the course also here. This one and this one, both. And if you have time, take a look at this information here. Finite element programs are very important for you as mechanical engineers. So please try to read. Okay, you have no more courses, so you have time today. I understood. That's correct?
Yes.
I must go at school right now, so see you next week. And in my opinion, till next week also, if you finish the first and two lab, please send it by mail. My mail is here. My mail address is here. Where I'm.
Can you make the assignment on Moodle so that it's not restricted? Only it has a deadline.
I will
So
try.
that if I finish it tomorrow, I can upload it tomorrow, not wait until.
Okay. I will start. Let's say today, but the deadline will be.
Yes.
In 1 month for this third lab. Okay, and after that, you must finish in time. Let's say not 12, but 1 p.m. or 2 p.m. Yeah, let's say that now in online it's a little bit difficult because you must write, you must transform the document in a file or another file, but better is to use PDF file. So if necessary, please use this email address to send me directly the lab 1 and 2. Yeah. Okay, that's all for today. May I close the recording here? Oh.